Hi guys, here is two examples of some quadratics application problems. So when we talk about these application problems, we're just incorporating sort of a real life context to some of these quadratic problems. So we'll talk about the pieces that we're solving for, and so this one is pretty scaffolded. We'll go through step by step, and then the next problem is an optimization problem that we'll also go through step by step. So feel free to follow along. You can print this sheet out if you'd like to really follow along as we go through, and you'll see listed below the video, the link for the video, that there is a homework assignment from your textbook. So we have Cam went golfing last weekend and made a hole-in-one. Yay, Cam. He had his friend Nick video the shot, and they worked together to find the path of the golf ball that could be modeled using the quadratic function h of t is equal to negative 16t squared plus 64t, where t is the number of seconds elapsed since Cam hit the ball, and h of t represents the height of the ball. So part A says, make a table for the above given quadratic and plot a few of the points on the graph to the right. So if you were to go ahead and grab your graphing calculator, you could type this into your y equals, and you could make a table of values. So you could go ahead and type in negative 16 x squared plus 64t. So I'm actually doing this sort of along with you. And if you hit second table, it will bring us to a table of values. And let's see, I will go ahead and insert a sticky here off to the side. Let's insert my sticky. So it looks like this. So I will have some x values and some y values, or some t values and some h of t values. So my graphing calculator will spit out a lot of different values. It will spit out some negative values here, and if I look at sort of my xy axis or my coordinate plane that I've been given here, I don't have any negative values. And that's because A, we're talking about time here, so time, we're not going to reference time as a negative value. And B, we're talking about height. We're also not going to reference height as a negative value. So I'm going to start here at 0, 0. If I plug in 1, I'll be at 48. 2, I'll be at 64. 3, I'll be at 48. 4, I'll be at 0, and 5 actually puts me into negative 80. So these are the values that I'm going to use here, and these are the values that I'll go ahead and plot. So here I'm at 0, 0. I'm going up to 5. So let's say I have 1, 2, 3, 4, and 5. And it looks like I need to go up to 64. Let's go up here by 5. So here I'm at 5, 10, 15, 20, 25, 30, 35, 40, 40, whoop, that's a 40, 45, 50, 55, 60, and I'm here at 65, 70. Awesome. So now I am going to go ahead and plot some of these values. So here I have time, and here I have height. And this is the path of Cam's golf ball. So I'm here at 0, 0, and let's maybe do this in a color that's a little bit brighter. Here I'm at 0, 0. And then I'm over at 1 and up at 48, over 2, and I'm up at 64, over 3, and I'm up again here at 48, and 4, I'm at 0. So if I were to go ahead and sort of roughly sketch this in as a parabola, this is what my value would look like here. And I'm just going to get rid of this so I have a little more space. So here I plotted a few points, and we can see that over to the right. What is the maximum height of the ball? So this is what I was talking about, sort of if you read the Canvas instructions here. We've graphed a lot of these quadratics. The maximum height of the ball, seeing that this is a concave down parabola, the maximum height here is going to be my vertex. And so I have sort of two coordinates to my vertex, and it looks like my vertex is 2, 64. So 2 is the time, and 64 is the height. So the maximum height of the ball is 64. Are we talking about feet here? Yes, I will say we are talking about feet. 64 feet is the maximum height of the ball here. How long is the ball in the air for? So how long is asking for an x coordinate. So the ball is in the air, so here it's leaving Cam's sort of golf club. It's traveling up, it's hitting its maximum height, and then it's coming back down. The ball is in the air for 4 seconds. So this is another way of saying, what is that x-intercept? This part B question was a way of saying, what is that vertex? How long does it take for the ball to reach its maximum height? This is a fancy way of asking for the x-coordinate, or the axis of symmetry, the x-coordinate of the vertex. We would say 2 seconds. For how many seconds is the ball more than 48 feet in the air? So 48 feet is my y-axis here, 48 feet. So here is where my ball hits 48 feet. So I would say that from here all the way to here, my graph is in the air, or my ball is in the air for more than 48 feet. So between 1 second and 3 seconds. So we would say that the ball is in the air for more than 48 feet for 2 seconds, or between 1 second and 3 seconds. So this is just a way of sort of applying a context to this quadratic problem. So instead of saying what is the vertex of this parabola, we could say what is the maximum height of Cam's golf ball. So these problems can get a little tricky, but thinking about which piece of the parabola that you're trying to solve for is the best way to go about doing these problems. So let's move on to Farmer Chris. Farmer Chris has 2,000 feet of fencing, and he wants to enclose a rectangular plot for his animals that borders a river. If Farmer Chris does not use any fencing along the side of the river, what are some of the dimensions that he could have to use all of the fencing? So we're saying that we have 2,000 feet of fencing. We are using all 2,000 feet so that these animals can have the biggest area and perimeter possible. So, what is the largest area that Farmer Chris can use for his animals? So let's just go ahead and say, let's give ourselves some examples. We're only using fencing on these 3 sections because this is my river. And I'm looking for the largest area. What are some of the dimensions that he could have to use all the fencing? And then sort of the follow-up question is, what is the largest area he could create for his animals? So thinking about here, I would have a sort of a length and a width here, right? So let's call this sort of an X, let's call this W and L. So if my width is, let's say, 20 feet, then this is 20, and this is 20, and this would be 2,000 minus 40, which will put me at a length of 1,960. Right? Are we seeing how we're getting these values here? So we could go ahead and just keep brainstorming here. Brainstorming different lengths and different widths. But really what I'm looking for is the largest area. So let's go ahead and brainstorm one more. What if I had a width of 40? That would make this 40 and this 40, and this would be 2,000 minus 80. Because I want everything to add up to 2,000. So this would be 1,920 feet for my length. So looking here, if this is my length and this is my width, what is my area? So 20 times 1,960. This is going to give me an area of 39,200 feet squared. And let's see, do I get a different area here? 1,920. Yeah, my area is much larger if I have a larger width. So let's say I went to 50 or 60 or 80, right? At some point, my width would start getting larger than my length, and I would end up sort of making a different shape here for my fence. So thinking that our overall goal is to get the largest area, let's see if we can create some sort of equation here. So let's see. Let's suppose that our width here is W. So let's suppose that our width here is W, which we already have. So I have W and W. And my length, let's call my length exactly what we've been calling it. 2,000 minus 2 times W. So the area here is W times 2,000 minus 2W. So it looks like I've created this new equation here, and if I go ahead and distribute my W, my area is negative 2W squared plus 2,000W. And I know that this will end up giving me a concave down parabola where W is my x value, which is the width of my rectangle, and my sort of y values here represents the area. I also know that this is plus 0, right? There's no constant here, so it's 0, which means that my function is passing here through 0, 0. It's going to be a concave down parabola, and it will eventually come back down. So thinking about where the maximum area could potentially happen here, that's going to be at the vertex of my parabola. So I can go ahead and solve this. A equals negative 2W squared plus 2,000W. I can solve this sort of however I would like for the vertex of my parabola. So I can start by using x equals negative b over 2a, or w equals negative b over 2a. So w equals negative 2,000 divided by 2 times negative 2. So here I get negative 2,000 over negative 4. And when I go ahead and do that, that's going to give me a width of 500. So here I have a width of 500 up here. And I also have a width of 500, right? Because W on one side is the same as W on the other side. So if that is my width, then I know that my length is 2,000 minus 2 times 500. So my length becomes 1,000, and my area of my rectangle becomes 500,000 feet squared. So we can sort of compare this to these values that we started to see up here, and this area is much, much larger than what we had originally found. So looking for the largest area, we would call this problem, it's certainly an application problem, but also an optimization problem. We're looking for sort of an optimal value. So when we talk about these optimization problems, we're either looking for a maximum or we're looking for a minimum. And whenever we're talking about these quadratic functions, my maximum and my maximum is always the vertex of my concave down parabola, and the minimum is always my vertex of my concave up parabola. So going back to sort of thinking about which sort of important pieces of the parabola that you're trying to solve for. And typically we're always looking for something like a y-intercept, a vertex, or an x-intercept.